in part 1, we saw the recipe of how to expand with partial fractions. And now in part 2, this video, we're going to go ahead and show you how to actually do the expansion and solve for the coefficients. So let's jump into it. By the way, new microphone, so hopefully things will sound all right. Let's hope for the best. So in all of these, except for E, because that one has a lot of unknowns. That one has 6 unknowns, A, B, C, D, E, and F. What we're going to do is we're actually going to go ahead and describe the procedure on how you actually solve for these coefficients, A, B, and so on. So let's go ahead and just jump into the first one here. I have my notes off to the side here. So let's see how we can do partial fractions. So for the first one, we have the fraction. Okay, this is 1a. We have 1 over x minus 1 times x plus 2. And we saw from above that we can actually expand this as some number a over x minus 1 plus some number b over x plus 2. And now, of course, the natural question is, how do I go about in actually solving for these coefficients a and b? So remember, this is supposed to be an equation, an unknown equation, in a and b. Okay, x is there as a parameter, an intermediate variable if you like. And what we need to do first, as I copy here, okay, so let's just copy and paste stuff in and just fix as we go along. Okay, so what we'll need to do, okay, this is A and this is B. I'm going to go ahead and multiply both sides of this by the common denominator, x minus 1 times x plus 2. I'm going to go ahead and clear fractions on both sides. Okay, and we have to be very careful to do the distributive property here very carefully. So each thing gets multiplied by both of these. Okay, so let's go ahead and indicate that. And let's write down what the multiplications come out to be. Okay, so on the left-hand side, okay, we have the same factors there, so everything vanishes. We just have a 1. And on the right, when we go ahead and expand, well, let's just write it out here. We have a times x minus 1 times x plus 2. That's over x minus 1. And now we have b times x minus 1 times x plus 2 over x plus 2. And we see that the correct stuff will vanish on the right-hand side. So the x minus 1s drop here, the x plus 2s drop here. And now I'm left with 1 equals a times x plus 2 plus b times x minus 1. So we have an equation in a and b in the intermediate variable x, and I need to solve this for a and b. That gives me the identity above here. So there are a couple of ways to do this, and the one that I'll show for the first couple of problems here is the so-called Heaviside cover-up method. And what this is because that this is an identity, okay, this has to hold for all x. So meaning I should be able to plug in whatever x value I want, and of course, you know, modulo a domain issue, which we won't really worry about here for the moment, everything will make sense. So how do we handle this? Well, let's go ahead and see how that works. We want to pick some clever values. Okay, so we'll pick some clever x values. And what that means is we'll pick something so that one of the terms will vanish. Well, if we look here very carefully, we see that if I set, say, x equals 1, well, then the b term will vanish, because if I plug in 1 there, right, 1 minus 1 is 0, 0 times b is 0. So if I plug in 1 on both sides, I'll get 1 equals a times 1 plus 2. Well, I get 1 equals 3a. And so if I divide both sides by 3, I solve for a. A is equal to a third. So that's how that works out. And what's the other clever x value that I want to select? Well, what's something else that'll make a term vanish? And you probably could guess here. Okay, if I set x equals to -2 now, well, then the a term will vanish. So by doing that, I'll still have a 1 on the left-hand side, but on the right, I will have, let's write this down, b times -2 minus 1 Negative 2 minus 1 is a negative 3, so I have 1 equals negative 3b. And dividing both sides by negative 3, we get b is equal to minus 1/3. So what is our partial fraction decomposition in the end? Okay, so in the end, we have found our weights, okay, these unknown coefficients. And so what I can do, just replace the values here. So a was associated with the x minus 1 factor, so a is equal to 1/3, b is equal to negative 1/3. And you can also, go ahead and put that minus sign where it goes. I would stick with this. Okay. But now take a look. This is so much easier if I were to actually integrate this. This is so much easier, right? Instead of integrating the hard fraction on the left-hand side, I can integrate the two easier fractions on the right. Okay, this is the idea of partial fractions. All right, so let's go ahead and move on to our next one. Our next fraction here I have to consider, okay, this is 1b here. We have x squared minus 3, plus 3x, plus 3x minus 4 over 2x minus 1 squared times 2x plus 3. Now, let's remind ourselves what the recipe looks like here. We have a repeated linear factor here in 2x minus 1. So I'll have a over 2x minus 1. And then to account for the second copy, I'm going to add in another power of 2x minus 1 there. So we count up, okay, to the repeated factor. And then the last factor only appears once, so we just get c over 2x plus 3. And so this was our recipe. Okay, let's go ahead and I'll just copy this through. So it's lasso, and I think that'll do the job. Okay, here we are. And now what we're going to do is, again, multiply through by a common denominator. So we'll go ahead and multiply through by the denominator there on the left-hand side. So both sides get multiplied by 2x minus 1 squared times 2x plus 3. Let's go ahead and put that like that. And we'll do the same here on the right. So 2x minus 1 squared times 2x plus 3. Okay, I'll go ahead and write out what the distributive step looks like, and you'll see that some stuff vanishes pretty nicely. So when we multiply through, so on the left, I just have the numerator, x squared plus 3x minus 4. And on the right, let's write out what we get with the distributive property here. So a times 2x minus 1 squared times 2x plus 3. And hopefully you'll be able to see the pattern, so you don't have to write this down every time, but it's a good idea to write this down. Okay, then for the b term, same type of numerator. And in the denominator here, 2x minus 1 square. And finally, still have the same numerator here for c. And on the bottom, we have 2x plus 3. So let's go ahead and mark out the things that actually will vanish. So for the first term, I have one of the 2x minus 1s going away. In the second, both the 2x minus 1s go away. And in the third, the 2x plus 3 goes away. So I'm left with here a times 2x minus 1 times 2x plus 3 plus b times 2x plus 3 plus c times 2x minus 1 squared. Okay, so this is what we're left with. And now we go ahead and do the same procedure as before. We're going to find some clever x values so that stuff can vanish. And, now we can just solve some basic equations. So if you've noticed from above, okay, the way that I selected those clever x values is making some of those factors be 0. Okay, so what we're going to do as an aside, okay, we need to set the two factors equal to 0. So 2x minus 1 equals 0. And 2x plus 3 equals 0. This will give us our clever x values to select. So, you can do the work here. You'll get x equals 1/2 as the first clever x value. And the second, x equals minus 3 over 2. So those will be our two clever x values that we will select. So for the first one, let's just go ahead and put in x equals 1/2 And remember, we're going to do this on both sides, okay? Everywhere that there's an x, we're going to replace it with a 1/2 here. And I won't bore you with the laborious details. I have it written down here, but after we plug in 1/2, okay, that means all the 2x minus 1 factors will go away. So we have an equation for b, and on my paper, I have that as, let's see, we have negative 9 over 4 equals 4b. And when I divide both sides by b, I get that b is equal to minus 9 over 16. Okay, so that's straightforward enough. For the second clever x value, x equals minus 3 over 2. That means all of the 2x plus 3 factors will go away. And this will leave me with an equation in C. Okay, so when I do that work, again, plugging in minus 3 over 2 into both sides, I have, let's see, negative 25 over 4 equals, and when we do the work there, we'll get a 16C. Let's fix that a little. Okay, 2 times negative 3 over 2, that's a negative 3. Minus 1 is a negative 4. Square that is a positive 16. And now, when I solve that equation for C, I get that C is equal to minus 25 over 64. Now, some of you may be wondering, well, I have 2 clever x values, but I have 3 unknowns to solve for, so how do I get the third? Well, remember that this is an identity. So I can do this for any x value I want, okay? Just some are more convenient than others. When you run out of ones to choose, we'll try to pick some of the next best ones. And what I'll do here is actually I'll select x equals 0. Now, why is that? Well, you know, what's 0 squared? What's 0 times any non-zero number? Well, 0 times any number is 0. 0 squared is 0. So it just makes my life a little easier. And plus, I can already use the fact that I solved for b and c, okay, to figure out how to solve for a here. So if I plug in 0, x equals 0 on both sides, on the left, we get a negative 4. And on the right, well, let's see what we have here. Well, plugging in x equals 0, I'll get a negative 1 times a 3, so that's a negative 3 times a. Okay, now plus, let's go ahead and just write out the rest of this. So if I plug in 0 into the next bit, I get a 3b. And then plug in a 0 into the next bit, well, negative 1 squared is a positive 1. I get a plus c. Okay? Now, I already know what b and c are. So I can just go ahead and toss those in, right? I can just go ahead and toss in those values for b and c. Now, of course, we'll get some fractions here. You can use your favorite calculating device. Just be a little careful. When you go ahead and collect everything, okay, you'll be doing a bit of work here. So after you've replaced everything, in fact, let's just go ahead and show it. So negative 4 equals negative 3a. That's the unknown. And then plus 3 times b, so 3 times negative 9 over 16. And then plus c, which is negative 25 over 64. And when I combine all the fractions and shove stuff over, okay, what I get, okay, in the penultimate step, negative 123 over 64 equals negative 3a. All right, and the mating move, divide by negative 3. So we get that a is equal to, let's see, 41 over 64. So we've solved for a, b, and c. And now what does that tell us? Well, if we go back to our original decomposition here, our recipe, all we have to do is just plug in the appropriate parts here. So let's go ahead and do that. So let's see. A is 41 over 64. B is, let's see. B is negative 9 over 16. And C was negative 25 over 64. Okay, now of course, once I have all the constants there, okay, this thing on the right is so much easier to integrate, which is the goal in the end, okay? The 2 outside integrals, the 2 outside terms will give me logs, okay? Just be very careful with the change of variables, okay? Chain rule, use substitution. But the one in the middle is going to end up being something times 2x minus 1 to the negative 1 power. Why? Because of the power rule, okay? Again, no calculus yet for this part, but I want you to look ahead, right? What are we trying to do? We're trying to integrate these kinds of functions. All right, so let's move on to 1c. 1c, we started looking at some, no quadratics yet, but this is another one of those repeated linear factors here. So let's take a look here. So I roll up my sleeve here. So for that one, we have 1 over x to the 4th minus x cubed. Okay, and remember that I had to factor my denominator, okay? So when I factor, I get an x cubed, and then an x minus 1 left over on the bottom. And what's our recipe for this one? Well, for this one, okay, we are trying to get this. So we have one linear factor that has 1 copy, and another that has 3 copies, okay? Remember that x cubed is just x minus 0 all cubed. So we have a over x plus b over x squared. That's the repeat. And then one more repeat. Okay, count up, x cubed. And then lastly, d over x minus 1. Okay. So now how do we set this up? Usual game. Let's go ahead and lasso this one here. Okay. And I'll go ahead and write out the step that we need to do, which is, of course, multiply both sides by the common denominator. Write it like this. Okay, but I won't write down the distributive part. Okay, I encourage you to do that on your own here. We'll multiply both sides by x cubed times x minus 1. X cubed times x minus 1. Okay. And when we do this, on the left-hand side, we get a 1. And on the right, what do we get? Well, after you've gone and done all the multiplications, you'll have a times x squared times x minus 1 plus b times x minus 1 plus c times x minus 1 plus d times x cubed. Again, this was part from a recipe. Now, go ahead and notice, okay, that this is 4 things, but I only really have 2 factors to work with. So the clever substitution thing can still work. You just got to work a little harder for it. And I think this is a good time now to demonstrate the second way of doing these partial fractions decompositions, which is just by setting up a system of linear equations. And so I'm going to go ahead and continue to multiply the rest of this out, okay? So let's see here. We have an ax cubed minus ax squared plus bx squared minus bx plus cx minus c plus dx cubed. Now, why did I do that? Well, remember, this is supposed to be an identity, right? And so that means if these two are supposed to be equal for every value of x, then that means I need the same number of each power on both sides. What that means is I need the same number of 1s, the same number of x's, the same number of x squares, and the same number of x cubes, okay? So we're going to go ahead and set up a system of linear equations. So I'll need 4 colors here. Let's go ahead and take a look at the constant term first. That's probably the easiest one here, so I'll do this in yellow. So on the left, I just have a 1. Okay, I have 1 there. But on the right, well, how many constant terms do I have here? Well, on the right-hand side, the only constant term that I have here, something without a power of x, is just negative c. Okay, so I'll go ahead and write this equation in a slightly darker shade of yellow, because it won't show up as well on camera. So for the constant term, we have that negative c is equal to 1. And immediately that tells us that c is equal to negative 1. Okay, so, well, now what? Well, let's go ahead and take a look at the next equation that we would need to set up. On the left, notice that I don't have any x terms. But on the right, what are the x terms that I have? Well, I have a negative bx and a plus cx. So if I extract the coefficients there, negative bx plus cx, so let's write that down here, negative b plus c times x, okay? Well, I have no x terms on the left-hand side. So negative b plus c should be equal to 0. But the fun thing is, I already know what c is. So if I take that and substitute it in, we're basically doing a bunch of back substitution, okay? This is like the easiest kind of system of equation that you can do. If you can solve for one and back substitute, very nice. But your general methods of solving linear equations will work here. So elimination, substitution, you can check that in your favorite college algebra, pre-calculus, or even your favorite linear algebra text. So if we go ahead and go back here, we'll get that negative b minus 1 is equal to 0. We do a bit of shuffling and not pinching in on the paper here. There we go. So negative b minus 1 equals 0. When I shuffle some things around, we get that b is equal to negative 1. Excellent. Okay, and that makes sense. Negative 1, okay, for b means that we have negative b, so that's 1 minus 1 is 0. Everything works out. All right, new color here. Let's try this light blue here. Let's look at the x squared terms. Now again, I have no x squared terms on the left, but on the right, I have negative a x squared, and then plus bx squared. So again, just extract the coefficients here, and what do I get? If I extract the coefficients, I get negative a plus b. That should also be equal to 0, because there are no x squared terms on the left. Well, just do what we did, right? Take our value for b that we solved for previously. Negative a minus 1 equals 0. Shuffle some stuff around, not pinch in. This is going to be a recurring theme. A is equal to negative 1. Okay. So again, we're building up this. This is actually an easy type of system of equations to solve. Now let's go ahead and take a look at the last one. Again, there are no x cubed terms on the left. Let's do this in magenta. But on the right, ax cubed plus dx cubed. So that means that I should have a plus d should be equal to 0, because there are no x cubed terms on the left. Okay, well, do what we did before. Take our value of a, plug it into this one. We substitute what we know. Negative 1 plus d equals 0, and that tells us that d equals 1. Okay, so d equals 1. And now, what do we have for our partial fraction decomposition? As I untangle myself here. Well, let's go ahead and put that back here. So, here is our general recipe. And remember, we wanted this to be equal to, let's see, we wanted this to equal 1 over x cubed times x minus 1. Okay, now let's go ahead and plug in everything. So let's go ahead and scroll so I have all the pieces here. A is equal to negative 1. B is equal to negative 1. C is equal to negative 1. And D is equal to positive 1. And that's how we get our partial fraction decomposition for that one there. And you can probably now see that the thing on the right is so much easier to integrate. Isn't it fun? So that's how we do that one. Again, you can go ahead and do the system of equations. Sometimes it works out nicely like it does in this one. But you can also do the clever cover-up method. This one may have taken a bit longer for the cover-up because you'd still have to ultimately solve another system of equations, but it'd be 2 equations and 2 unknowns. And again, for that, for just how to solve systems of equations in general, just go ahead and consult your favorite algebra reference. We got one more. Okay, this was the one where we had some quadratics in there. Okay, so for this last one, we wanted to look at, let's see here, x squared, that's a minus 2, over x times x squared plus 2. Now again, because I have a sum of squares in the denominator, okay, at that x squared plus 2, remember that I started over this, what really irreducible really means you can't factor it over to real numbers. But anytime you see a sum of squares, x squared plus a squared, here a just happens to be the square root of 2, okay, that means you have an irreducible quadratic. You can't break it up into a product of two linear binomials that have real numbers in them. And so at worst, you just have to have a numerator that is, well, linear. So we saw that our recipe for this one was a over x plus now bx plus c over x squared plus 2. Okay, that was our recipe. Again, remember, because of the irreducible quadratic in the x squared plus 2, at worst, the numerator for that one is going to be linear. Okay, it may be the fact that c could be 0 or b could be 0, but certainly not both. All right, so now let's just go ahead, lasso this again. All right, and we're going to multiply once again by the common denominator. We have x squared plus 2 times x. Okay, multiply that on both sides here. Okay, so now we go ahead and write out what we get. On the left, x squared minus 2. And on the right, we'll get a times x squared plus 2. And once again, go ahead and do the multiplication, set it up like I did in the first couple, and make sure that you get the correct terms that remain. And on the right, we have bx plus c times just an x left over. Okay, so we're going to go back to the cover-up method here. Again, I could go ahead and do some equating of coefficients here, which is what we did in the last one, set up a system of equations. But I'm going to go back to the cover-up method just to, again, demonstrate that one. So one of the values that can definitely be selected here, I can definitely select x equals 0 because I had a lone x factor. Okay. So if x equals 0, on the left, I get a negative 2. And on the right, I get, well, 0 squared is 0, plus 2 is 2. So 2a. But what about the other stuff? Well, 0 times anything is 0, so this is the only thing that I have. So when I divide by 2, I get that a is equal to minus 1. Okay, now we gotta work a little harder here, okay? So this is, again, where the cover-up method can kind of end up being a little finicky. Okay, we're still going to have to solve a system of linear equations. So let's go ahead and see what happens when we set x equal to 1. Well, on the left, 1 squared minus 2 is negative 1, okay? And on the right, let's just go ahead and write out everything here. 1 squared is 1 plus 2 is 3, so 3a. And then I have a plus b plus c, and then times 1, because we have a positive 1 there. Let's just write that down. Okay, now, and what's the other one that we select? Let's go ahead and select x equals negative 1. It'll still work out nicely. Give ourselves a bit more room here. So if x equals negative 1, well, on the left here, negative 1 squared is still a positive 1, but 1 minus 2 is negative 1. On the right, negative 1 squared is 1, plus 2 is 3, so I still get a 3a here. Now take a look here. We're going to be a little careful here. I'll have a plus, well, b times negative 1, that's negative b, plus c, times a negative 1. Let's tidy up that up a little. So we get 3a. I'll have a minus here. Okay, minus negative b plus c. Okay. All right. Well, we already know what a is, right? Okay, a is negative 1. So I'm going to go ahead and do some cleaning up here. A is negative 1. So remember, we had negative 1 times 3, so negative 3, negative 3, negative 3. Now I'm going to take these two equations here and watch what will happen. If I shove the negative 3 over by adding the inverse operation, well, I get, for the first equation, b plus c equals 2. And then for the second, well, let's see. Negative 1 plus 3 is a positive 2. But take a look here. I still have this negative here, so I divide by a negative 1. Okay? So let's do this very carefully here. B, nope, already messed up. Negative b plus c equals, well, here's what we would have, okay, in the step before. 2 equals negative of negative b plus c. Then now I divide by a -1. So I get a -2 there. 2 equations and 2 unknowns. You can solve this however you like. Elimination, substitution. Okay, for me, I can easily spot it. If I add these 2 equations, okay, if I add these 2 equations, take a look at what happens. Just add them column-wise, right? B minus B is 0, so those vanish, those eliminate. C plus C is 2C, and 2 minus 2 is 0. And guess what? C is 0. C is 0. Now I plug that into either one of the equations. No matter what I do, I get that B is equal to 2. And so what's our partial fraction decomposition here? We found A, B, and C. And like I said here, C ended up being 0. So our decomposition, okay, now that we can erase some stuff here. So C is 0, A is -1, B is 2, and C is 0. And folks, that right there is our breakdown of that hard fraction on the left. On the right, much easier to integrate. Try to see what you could do for the integral in the second, okay? But we'll see actually how to integrate these in part 3, okay? But now that we see the method, which is just all algebra, we're going to go ahead and make the connection to how to integrate these rational functions in part 3, where we now talk about some basic examples. And I'll see you in the next one.